In this video, we're going to look at the moment approach to prior selection. And this approach applies when the capital lambda family of priors under consideration follow a given functional form, and also when it is possible to relate the prior moments to the moments of the marginal distribution. And we'll see that as we go along. To start, though, let's look at this definition and remind ourselves about the difference between the kth moment and the kth sample moment. So here we have our random sample, and the kth sample moment is what we see here, where we just add up our xi's to the power k and then divide by however many we have. So m sub 1 prime here would be the regular sample mean, x bar. And as usual, we denote the kth moment as we see here. And notice here, in terms of notation, we subscript the k that indicates which moment we are referring to. And the method of moments is a simple method for deriving estimators for our parameters, and all we do is just equate the kth moment and the kth sample moment, and then just solve for the parameter involved, and whatever that leads to is the estimator that we will use for that. So let's look at an example. So here we have a random sample from a normal distribution. And so let's use the method of moments to estimate the unknown parameters mu and sigma squared. So note that the first two moments are given by what we see here. So we're taking the expectation with respect to our x1 given mu and sigma squared. And then the second moment given mu and sigma squared would be mu squared plus sigma squared. We've seen that several times. So now what we're going to do is replace mu and sigma in this expression by mu hat and sigma hat, and then equate each one of those to the sample moments, and then solve that system of equations. And then that leads to the standard estimate for mu, which is x bar. And then here is not what we typically call the sample variance, but very close to that. It can be a little difficult to get this form of the solution here for sigma hat squared, so I thought I would talk a little bit about how to do that. You can see from here that mu hat is just x bar, and then it's easy to solve sigma hat squared from there. But y is that equal to this can be a little challenging. So from previous, we can see this solution here. And then here I'm going to replace mu hat with x bar squared, and then also put this in parentheses to emphasize that the summation doesn't apply over here. And then we should be able to easily see that this is true. So then y is that equal to this expression we have here. And so I think the easiest way to do it is to start from this expression and multiply it out, and then focus on this middle term. So let's move this middle term out. So let's keep these together and then pull out that middle term like I said. And notice that since x bar doesn't depend on the index of summation, I've pulled it out in front of the summation. And now let's just focus on this part. So remember that the sum of the xi's is the same as little n times x bar, so replacing that here, then we get this expression here. And now if we put all of this back together, we essentially can replace this part here with 2x bar squared. And from there, I think you can see that these two are the same. Okay, so in order for us to do this moment approach to prior selection, we're going to have to use this lemma that's provided by the textbook. First, we have here some notation for the conditional moment of x given theta, the conditional mean of x given theta, and then also the conditional variance of x given theta. And also let's notate the marginal mean and variance as we see here. And as we mentioned earlier, we're going to have a way to connect these things together, and that's given below. These are essentially conditional formulas that are used in statistics a lot. This first one is sometimes called the double expectation formula, and then the second one is called the law of total variance. And we won't go through the proof of that, but we will use those. Here is a problem that we looked at earlier when we were learning how to calculate the marginals and to use the marginals to help us assess the prior distribution. So we have x sub I given theta sub I is normal distribution with mean theta sub I and variance sigma sub f squared. And that sigma sub f squared is known as indicated there, but the mean is actually we're going to treat as random. And you can see here we have a whole parameter vector of these means. So the data here does not constitute a random sample. We mentioned that in the previous video. And so we're supposing that each theta I is IID with a common distribution that we see here. So a normal distribution with mean mu sub pi and variance sigma sub pi squared. And both of those are unknown. And in this example, we're going to use the method of moments to estimate mu sub pi and sigma sub pi squared. At this point, this would be a good time in the video for you to pause and see if you can use that formula that we just covered in the lemma to verify what we determined earlier in the previous video, and that is that the marginal mean is equal to mu sub pi, and the marginal variance is equal to sigma sub f squared plus sigma sub pi squared. Okay, so from the lemma and the previous example, like I said before, we can calculate the marginal mean using the double expectation formula, which is from the lemma. And so we're taking the expected value with respect to our theta of the conditional mean of x. So this inner part is the conditional mean of x1 given theta 1. And then once we calculate that, we're going to be left with an expression involving theta 1, and then we take the expectation of that. So the conditional mean of x given theta is theta 1. And so that gets us this part here, and then we take the expected value of theta 1 according to the prior distribution, which gives us mu sub pi. Because remember, that was a normal distribution with this mean mu sub pi. Okay, now we can calculate the marginal variance using the law of total variance, which is the second formula that we got from the lemma. So first, we look at the conditional variance of x given theta 1, and then we take the expected value of that using our distribution on theta, and then we add to that this expression here, which is the variance with respect to theta of the conditional expected value of x given theta. And in this next line, I think we can see the law of total variance formula more clearly, because we're taking the expected value of the conditional variance plus the variance of the conditional expectation. And then the variance of the conditional is sigma sub f squared, and so we get this part here, and sigma sub f squared is known, so that expectation is just sigma sub f squared, and then plus the expected value of x1 given theta 1, well, that's theta 1, and then now we need the variance of theta 1, which is this part, sigma sub pi squared. Now at this point, let's recall that previous example where we learned that the standard moment estimators for the mean and the variance are what we see here. Now, if we apply that to the example we're working on, then the standard estimate for the marginal mean is x bar. So we can use that to estimate the prior mean. And then the standard estimate for the marginal variance is little s squared, as we defined in that previous example. And so in the context of looking at this from the point of view of the prior, we can set this equal to s squared. And since it's really the prior parameters that we're after, then we'll put hats on these prior parameters, set the first one equal to x bar, set the second one equal to s squared, and then we get what we see here.